Welcome to the 29th lecture of the MOOC on parallel algorithms. In the previous lecture, we had started discussing the Hypercube architecture. Today, we shall see some properties of the Hypercube architecture, which establish that it is indeed a versatile architecture. In the last class, we saw that a linear array can be embedded on a hypercube, in the sense that a hypercube, when perceived as a graph, is a Hamiltonian graph. What this means is that there is a cycle of size n in a hypercube of n nodes. Of course, if there is a hypercube of n nodes, n is going to be a power of 2, and this hypercube is of dimensionality log n. So, in h log n, there is a cycle of size n. So, this is a cycle which passes through every vertex exactly once. What this means is that a linear array can be embedded in a hypercube. That is, if we are given an algorithm that runs on a linear array of n nodes and we are given a hypercube of n nodes, then this algorithm can be run on the hypercube without any change. That is because there is a linear array on the hypercube. A linear array is a subgraph of the hypercube. Therefore, we will activate only the edges that belong to this subgraph. So, these processors will work on the input. The algorithm will be run only on this subgraph. Only the edges belonging to this subgraph will be used by the algorithm. So, the algorithm will run exactly in the analyzed time. That is, the time it takes on the simulation is exactly the same as the time it takes on the actual run. What about higher dimensional arrays? This is the question we are going to address now. For this, let us define the notion of a cross product of graphs. First, let me give an example. Let us say we are given two graphs. This is one graph and this is another graph. This is G1 and this is G2. To take the cross product of these two graphs, what we do is this. We take, in the second graph there are 4 vertices, in the first graph there are 3 vertices. So, we will take 4 copies of the first graph. So, we have these 4 copies of the first graph. These 4 copies correspond to the 4 vertices of the second graph. In the second graph, we have 4 vertices. So, the copies of G1 correspond to these vertices. Now, we are going to introduce a bundle of edges in the cross product graph that correspond to the edges of the second graph. So, for every edge of the second graph, we are going to introduce a bundle of edges that go between the corresponding copies of G1. For example, for the top left to right edge of G2, we will introduce a bundle of edges between these two copies of the top 2 copies of G1, but then we will connect the corresponding vertices. We will connect vertices in this manner. The corresponding vertices are interconnected between the top 2 copies of G1. Similarly, the bottom 2 copies of G1 are also interconnected. but these two bundles of edges correspond to the two left to right edges of the top edge as well as the bottom edge. Then the two top to bottom edges will also be translated into two bundle of edges. So these will be between the left copies of G1 and between the right copies of G1. So let me draw those bundles using a different color. So here between the top left copy and the bottom left copy, we connect the corresponding vertices like this. Similarly here too. A graph obtained in this fashion is called the cross product of G1 and G2. It is denoted in this fashion. Now you can see that you could have obtained this graph by taking 3 copies of the second graph and connecting the corresponding vertices. You find that the graph that you obtain is exactly the same. Therefore, G1 cross G2 is identical to G2 cross G1. So this is a commutative operation. So in general, for two graphs G1 and G2, let us say we are given two graphs G1 and G2, where G1 has a vertex set of V1 and edge set of E1, and G2 has a vertex set of V1 and an edge V2 and an edge set of E2. Then we define the cross product of G1 cross G2 as a graph on V1 cross V2 with edge set E, where we define E as the set of all edges of this form the vertices of G1 cross G2 is the cross product of the two vertex sets V1 and V2, and then the edge sets are defined like this. From ordered pair U1 U2 to ordered pair V1 V2, we will have an edge if and only if either U1 is equal to U2, U1 is equal to V1 and U2 V2 is an edge of E2, the second graph, or U2 is equal to V2 and U1 V1 is an edge of the first graph. With respect to our example here, we have two graphs G1 and G2, where G1 is a 3-degree vertex and G2 is a 4-cycle. Then for a vertex U1 U2 and V1 V2 in this graph, we will have an edge between them precisely when U2 is equal to V2, which means they correspond to the same copy of G1, and then U1 V1 belongs to G1, or U1 is equal to V1, which means they are corresponding vertices of two 3 cycles, and U2 is equal to V2. So what we get is precisely this graph. So this is the cross product of two graphs. When we are given 3 graphs, we define the cross product of the 3 of them as you can readily verify that this is the same as this. In other words, the cross product of graphs is an associative operator. So this is an operator which is commutative as well as associative. Therefore, in general, we can write the expression G1 cross G2 cross G3 without parentheses. So the order of evaluation is not relevant. So why are we talking about cross products of graphs? This is because a 2D mesh is a cross product of linear arrays. To see this, take an example. Let us say we are given two linear arrays. one with 4 nodes and one with 3 nodes. What if we take the cross product of these? To take the cross product of these, we need to take 3 copies of the first graph G1, G1 is a 4 vertex node in this case, and then we have to connect the corresponding vertices. So, the vertices which are aligned vertically all are corresponding vertices. So, among these corresponding vertices we have to interconnect exactly as they are interconnected in G1 or rather G2. G2 is a linear array of size 3. So, G2 has 3 nodes that are interconnected to form a linear array. So, when we interconnect in this manner, what we get is a 3 by 4 mesh. So, what we find is that a 3 by 4 mesh is a cross product of a linear array of size 3 and a linear array of size 4. In general, for higher dimensions, a k-dimensional array with n1, n2, etc. dimensionalities for the mesh can be expressed as a cross product of a linear array of n1 nodes with a linear array of n2 nodes and so on. So, an n1 by n2 by etc. nk mesh is nothing but the cross product of these linear arrays. Now, why are we talking about cross products and what are we gaining by expressing multidimensional meshes as cross products of linear arrays? What we are going to achieve is this: we know that linear arrays embed in hypercubes. Therefore, we will be able to show that k-dimensional meshes embed in hypercubes because k-dimensional meshes can be expressed as cross products of linear arrays and hypercubes can be expressed as cross products of hypercubes. So, that is what we are going to show next. Consider H2, and H2 is obtained by taking 2 copies of H1 and interconnecting them in this manner. So, as you can readily see, this is a 2 by 2 mesh. A 2-dimensional hypercube is a 2 by 2 mesh. H3 is obtained by taking 2 copies of H2 and interconnecting the corresponding nodes as we know. You can see that this is nothing but a 2 by 2 by 2 mesh. So, continuing like this, we find that Hk in general is a mesh of this sort, a k-dimensional mesh where the dimensionality is 2 in each dimension. Therefore, in general we can say that a k-dimensional hypercube is a k-dimensional hypercube can be expressed as a cross product of graphs in this fashion. This is because Hk is a k-dimensional mesh of this sort. HK is a k-dimensional mesh of this sort. Now, this can be written like this. HK can be written like this. Where we have k hypercubes, k copies of H1 when operated under this operator will give us HK. This is because, as we have just seen, HK is a k-dimensional mesh of dimensionality 2 along each dimension. We can express this in this manner because of the associative property of the cross product operator. And so on until we come to the last group. Where the sum of the k's is k. But then, as we have just seen, when we take the cross product of k1 H1s, what we get is HK1. Therefore, HK can be expressed as the cross product of these graphs. Now, let us say we are given a mesh of this sort, an r-dimensional mesh with Ri as the Ki as the dimensionality along the ith dimension is given to us. This can be expressed as a cross product of La of K1, La of K2, etc. So, an r-dimensional mesh of this sort can be expressed as a cross product of several linear arrays of this form. Now, what we find here is this: LAK1 is a subgraph of HK1, and LAK2 is a subgraph of HK2, and so on, and LAKR is a subgraph of HKR. Now, HK is the cross product of these supergraphs, and the mesh M that is given to us is a cross product of these subgraphs. I will state here without proof that the cross product of G1 prime through Gk prime that are subgraphs of G1 through Gk is a subgraph of the cross product of G1 through Gk. This is easy to visualize, but I am leaving the formal proof to you. In other words, the cross product of G1 prime through Gk prime is a subgraph of the cross product of G1 through Gk. So, when we apply the principle here, what we find is that M which is a cross product of the linear arrays, is a subgraph of HK. In other words, since LAK1 is a subgraph of HK1, LAK2 is a subgraph of HK2 and so on, the cross product of the LAs is a subgraph of the cross product of HK1, HK2, etc. The former is nothing but M and the latter is nothing but HK. Therefore, what we establish now is that a mesh of this form is a subgraph of Why is that? When we are given a mesh of this sort, this mesh can be expressed as a cross product of linear arrays of size n1, n2, etc. up to nr. A linear array of size n1 is embedded in a hypercube of dimensionality log n1. A hypercube of log n1 dimensionality will have n1 vertices. Therefore, if you take a Hamiltonian cycle of this hypercube, it will have more than n1 vertices. So, n1 embeds in this hypercube. Linear array of size n1 embeds in this hypercube. Similarly, for all the other linear arrays, therefore, the mesh, which is a cross product of all these linear arrays, embeds in a hypercube of this sort. But this is nothing but a hypercube of these many dimensions. Therefore, a mesh of dimensions like this can be embedded in a hypercube of this sort. In particular, a 3×5 mesh can be embedded in a hypercube of dimensions ceiling of log 3 plus ceiling of log 5. Ceiling of log 3 is the same as log 4, which is 2, and the ceiling of log 5 is the same as log 8, which is 3. So, you require a hypercube of dimensions 5 to embed a 3×5 mesh. This establishes that a 3×5 mesh embeds in a 5-dimensional hypercube. But then a 3×5 mesh has only 15 processors. A hypercube of dimensions 5 has 32 processors. So, what we have established is that a mesh 3×5 mesh with 15 processors embeds in a hypercube H5 of 32 processors. That does not sound very impressive, because there is a smaller hypercube which might be a candidate for embedding a 3×5 mesh. There is a 16-node hypercube, which is H4. H4 has 16 nodes. Why don't we try to embed the 3×5 mesh in H4, which has 16 nodes? That would be more sensible, if possible. But then, as it happens, a 3×5 mesh does not embed in H5, in H4. It embeds in H5, but we are going to claim that it will not embed in H4. So, let us prove the statement that a 3×5 mesh does not embed in H4. Assume the contrary. Assume that a 3×5 mesh embeds in H4. Now, consider an embedding of the 3×5 mesh in H4, or in general any embedding of a mesh in H4. If you start at a vertex in a hypercube and then travel along some nodes in the hypercube and come back to the original vertex, then in the hypercube we would have traced every dimension twice. In every cycle of a hypercube, we will have to trace every dimension exactly twice. That is because the cycle completes the loop and takes you back to where you began. Therefore, every dimension will have to be traced back and forth. If you have crossed a dimension, you will have to cross the same dimension back to get back to the original point. Therefore, every dimension that you cross will have to be recrossed in the opposite direction. So, every cycle of a hypercube has this property: every dimension is traced an even number of times, traced exactly twice, once in each direction. In particular, if you consider a cycle of length 4, then you find that there are exactly 2 dimensions here, because any dimension that is crossed has to be recrossed. There can be only 2 dimensions in a cycle of size 4. So, if one dimension is of the 8th one and the second one is the bth one, then you have to retrace these dimensions back. But then at any node in the hypercube, there is only one edge of a particular dimension. So, if you consider this node here, it has only one edge of dimension b. Therefore, it is not possible to trace this edge, trace another b dimensional edge from this vertex. Therefore, all you can do is to take a dimension a edge from here and then complete the loop with a dimension b edge. Therefore, if you take any 4 cycle in a hypercube, there you find that 2 dimensions alternate, AB, AB. This is the only way you can have a 4 cycle in a hypercube. Now we have, let us come back to the embedding, the hypothesized embedding. We assume that we have a 3x5 mesh that has been embedded in a 16 node hypercube. So, let us consider the 3x5 mesh. So, as you can see, a 3x5 mesh has several 4 cycles. So, if you manage to embed a 3x5 mesh in an H4, these 4 cycles will correspond to some 4 cycles of the hypercube. Now, in particular, let me consider this edge. This is of dimension, this is along dimension A1, let us say. The marked edge is along dimension A1. That is, we assume that this 3x5 mesh is embedded in H4. Let it be that this edge is embedded along dimension A1. Then the vertical edge incident with that vertex, let us say, is along some dimension B1. Now, B1 is not the same as A1 because there cannot be 2 edges of the same dimension at any vertex. So, A1 is different from B1. Now, in any 4 cycle, the opposite edges are along the same dimension. Therefore, this edge will have to be of dimension A1 and this edge will have to be of dimension B1. Now, the same property tells us that this edge is also along dimension B1, so is this and so is this. Similarly, this edge is along dimension A1 as well. Now, at this node, we have 3 edges. 2 are along dimensions B1 and A1. The third one will have to be along a third dimension. So, this, let us say, is along dimension B2. I will use B's for the vertical dimensions. So, this edge is along dimension B2, let us say. In that case, these edges are also along dimension B2, because opposite edges of a 4 cycle are along the same dimensions. Now, let us look at this edge. This dimension will have to be different from both A1 and B1, and it will also have to be different from B2, because whatever dimension you assign to this edge, the same will be assigned to the edge here, which is adjacent to dimensions A1, B1 and B2. Therefore, this will have to be a 4th dimension. Since this is a horizontal dimension, a dimension assigned to a horizontal edge of the mesh, let me mark it A2. That tells us that these edges are also of dimension A2. Now remember, we are attempting to embed the 3 by 5 mesh in a 4-dimensional hypercube. So there are only 4 distinct dimensions, and we have already used up all 4 distinct dimensions A1, B1, A2 and B2. Therefore, if the embedding has to be possible, we will have to fill the remaining unmarked edges also with these 4 labels. Now coming to this node, we find that it has A2, B1 and B2 already assigned to the adjacent incident edges. Therefore, the only free dimension is A1. So this edge will have to be along dimension A1 if we do not want to use a 5th dimension. Therefore, these two are also along dimension A1. Opposite edges are along the same dimension in any 4 cycle. By the same argument, when we consider this node, we find that A1, B1 and B2 are already taken. Therefore, the unlabeled edge here will have to take A2. Therefore, this edge also will have to take A2. The bottom edge also will have to take A2. Now every edge is labeled. It would seem that an embedding has gone through, but it hasn't. That is because when I consider the top row, I find that along the top row, the dimensions alternate A1, A2, A1, A2. Now this has been embedded in a hypercube according to our hypothesis. But in that case, in a hypercube, when we start at any vertex and use exactly 2 dimensions A1 and A2 and use them in this order, when you go from the first vertex to the second vertex, you cross in dimension A1, then you cross in dimension A2, then you use dimension A1, you are crossing back in dimension A1, and then you cross back in dimension A2. In a hypercube, you would be getting back to the original vertex. When you cross in dimension A1, you are flipping the A1th bit of the binary representation of the label of a node. So you flip the A1th bit, then the A2th bit, then again the A1th bit, and then again the A2th bit. You will get the original representation back. So you have to be back in the original vertex, which means this vertex and this vertex are both embedded onto the same vertex of the hypercube, which is not possible. In an embedding of a graph into another graph, we have to map every vertex of the first graph into a unique vertex of the second graph. Here we find that 2 vertices of the first graph are mapped onto the same vertex of the second graph. The mapping has to be 1-to-1, which is not the case here. Therefore, such an embedding is not possible. So this is the contradiction that we have to write. So it is not possible to embed a 3 by 5 dimensional mesh in a 4-dimensional hypercube. So what we have seen is that a 3 by 5 mesh cannot be embedded in a 4-dimensional hypercube. Now let us see some other embedding properties of the hypercube. But first, let us see some symmetric properties of the hypercube architecture. Let us say we are given a permutation of the vertices. A permutation pi of the dimensions, not the vertices, the dimensions of a hypercube of r dimensions is given. So pi is a function that maps the sets 1 to R to 1 to R. So it's a permutation, so it's a 1-to-1 mapping. So this permutation is given to us, and in addition to this, let us say we are also given a pair of vertices. U and U prime. Then there exists an automorphism sigma of HR, so that sigma of u is equal to sigma of u is equal to u prime, and the dimensions of the automorphism permutes by pi the set 1 to r. That is, the original dimensions of the hypercube HR are permuted using pi in the automorphism. So, this is an interesting property of a hypercube. So, to explain this, let me first define what an automorphism is. An automorphism of a graph G is a mapping sigma from V to V. So, it is a renaming of the vertices of G, so that for two vertices u and v, sigma of u and sigma of v are adjacent in the automorphism, are adjacent in E, adjacent in graph G if and only if u and v are adjacent in the graph G. So, what it means is that if you rename the vertices of G using the function sigma, then what you get is exactly the same graph. For example, a trivial example would be a 3 cycle. Suppose these are the original names. If you rename the vertices in any order, we will get exactly the same graph. The same adjacency relation will be obtained. These are all the same graph. So, you can make this claim trivially for every single click, every single complete graph. And for some of the other graphs, this claim would be quite non-trivial. If some of the edges are missing, then making this claim would be certainly non-trivial. So, what we are claiming here is that for an r-dimensional hypercube, when we are given a permutation pi and a pair of vertices u and u prime, then there exists a renaming of the vertices of the hypercube in such a way that the dimensions are permuted according to pi and all the adjacencies of the hypercube are maintained. That is, even under the renaming, with the permutation pi of the dimensions realized, the graph would remain a hypercube. The adjacencies of the hypercube would remain the same. So, this can be shown like this. So, pi is the permutation given to us, u and u prime are the vertices given. So, what we want is this: we want the vertices of the hypercube to be renamed so that u gets mapped to u prime. We want sigma of u to become u prime, and the other vertices must be renamed accordingly so that two vertices that are adjacent in the hypercube will be adjacent even under the renaming. So, what we are going to do is this: we will effect a renaming of this sort. Let us say for a node x1 through xr, sigma is defined as the vertical bar denotes the concatenation operation, we use the exclusive OR operator here. So, a vertex that is labeled x1 through xr in the original hypercube will be relabeled in this fashion. The new label will be obtained in this fashion. The first bit of the new label will be the XOR of these 3 bits. You take the pi1th bit of X, the pi1th bit of U, and the first bit of U prime, take the XOR of these 3, that will give us the first bit of the new name of X1 through XR. So how does this achieve what we want? According to the permutation pi, the first dimension is going to occupy the pi1th position. And so on. When we are given a permutation pi of 1, 2, 3, 4, 5, 6, these are the original positions, original dimensions, and if the permutation pi is in this sort, of this sort, then the pi1th position will be occupied by 1, the pi2th position will be occupied by 2, and so on. So what we find is that when the renaming is effected in this manner, then the desired properties are achieved. So how exactly this will work, we shall see in the next lecture. So that is it from this lecture. Hope to see you in the next. Thank you.